milky white substance you see here is being separated from solution as a precipitate of silver chloride. This occurs as silver ions react with chloride ions to form the precipitate silver chloride. This basic reaction provides the clinical specialist with a method of determining chloride in body fluids. The chloridometer enables us to determine the chloride content of a sample in less than 1 minute. By controlling the release of silver ions and measuring a slight excess of these ions in solution after all chloride has been precipitated, we are able to time the reaction electronically. The procedure described is a titrometric method. Most titrations, however, involve the neutralization of acids by bases, using a specific liquid indicator to signal a color change at the endpoint. The chloridometer employs a coulometric titration. With this titration, a constant current is applied across silver electrodes. One electrode is the generator electrode and is physically consumed as silver ions pass into solution while current is applied. Free chloride ions in a test solution combine with the silver ions given off at the generator electrode to form the silver chloride precipitate. The rate of release of these silver ions is kept constant. When all the chloride has been precipitated, an equivalence point is reached. Additional generation of silver ions causes an increase in the electrical activity of the titrant. This causes a surge of current, which is sensed by the indicator electrodes. This surge marks the endpoint of the titration, since there are no more free chloride ions remaining to combine with the generated silver ions. The coulometric titration measures a quantity of electricity in coulombs at a fixed potential during a specific time. The number of coulombs generated, Q, is equal to the product of the current I times the time T. We say that Q equals I times T. Since the current is kept constant at the generator electrodes, the elapsed time of titration is proportional to the number of coulombs generated. The time necessary to reach the endpoint is taken as a relative measure of the chloride concentration in a given sample. Let us compare the concentration of known standard and an unknown by establishing a simple ratio and proportion of each with the respective times of titration. The titration time of an unknown is to its concentration as the titration time of a standard is to its known concentration. The ratio established should tell us the concentration of chloride in the unknown. Average blanking times are established for individual aliquots of diluent used in the titration. Blanking times allow for the lag time needed to establish sufficient current buildup in the titrant, as well as discounting any background chloride contamination in the diluent. This blanking time is automatically subtracted from the total chloride count of each sample before direct readout of chloride begins on the digital display. Samples are diluted with an acid solution of both nitric and acetic acids, plus a small amount of gelatin. Nitric acid provides good electrolyte conductivity. Acetic acid makes the solution less polar, thereby reducing the solubility of silver chloride. This provides a sharp endpoint. Gelatin enables a more uniform titration, since it is adsorbed to the electrodes. Thymol is added as an indicator in a ratio of 1 part thymol to every 60 parts diluent. Thymol turns pink in an acid solution. The acid environment aids in the prevention of silver chloride precipitation at the indicator cathode due to reduction potential at that point. Let's examine the chloridometer and familiarize ourselves with its basic operation. When the instrument is turned on, a pilot light signals its activation. Allow a 10-minute warm-up, during which time you can prepare dilutions of standards, control, and unknowns. The direct reader switch has 3 separate positions: off, blank, and titrate. When turned to the blank position, the digital display will read tenths of seconds for titration. This position is used to calibrate the blank time. The titrate position gives a direct digital readout in milliequivalents per liter of chloride in a given sample. The titration range switch has a low, medium, and high range of titration. The titration switch is kept in the high position for titration of serum, cerebrospinal fluid, and exudate chlorides. This position is dependent on the total titration time. In cases where low chlorides are present, the switch may be adjusted to slow down the rate of titration. The blank timer cues the instrument to begin direct readout only after the blank titration time has been subtracted for each standard and unknown titration. This delay circuit is activated immediately on cue to titrate and will start the direct readout circuit only after it has reached the zero position. The digital readout indicates both tenths of seconds and milliequivalents per liter chloride. As mentioned before, the choice of readout is determined by the position of the direct reader switch. Resetting the readout is done by depressing the reset bar. It is necessary to clear the meter reading after recording a result. A direct current ammeter records the amperage detected by the indicator electrodes in the titrant solution. Surging current at the endpoint causes the black indicator pointer to reach the adjustable red pointer. At the endpoint, a distinct click is heard as the relay switch is activated to shut down the digital recorder and generator electrode circuitry. The adjust titrate switch has two positions. Position 1 is the adjust position and activates the stir and reference electrodes. Position 2 is the titrate position and activates the generator electrode circuitry. To the left side of the front panel is the stir electrode assembly. This consists of two stationary indicator electrodes and two generator electrodes. The back generator electrode is stationary, while the front generator electrode is adjustable. Silver wire is fed into the adjustable terminal from an external supply that makes contact with the binding post electrical connection. The stir must move freely, and care should be exercised in making sure it does not brush against the generator wire. It is not necessary to clip the silver wire anode unless it is thinner than a straight pin. Clipping of the soft silver wire is best achieved with a pocket nail clipper. It is necessary to clean all surfaces of the electrodes with a water-soluble silver polish. Pay particular attention to cleaning the feet of the electrodes. Gently scrub tarnish and residue from them, and follow the cleaning operation with a deionized water rinse. Water droplets left from this rinse do not affect the titration, so do not attempt to dry electrode surfaces, since you will inevitably contaminate the surfaces with chloride. Let's prepare blanks, standards, and unknowns, and then describe the operation of the chloridometer. First, we prepare 4 blanks by delivering 4 milliliters of acid diluent to clean glass vials which have been properly labeled for identification. Next, we add 4 drops of gelatin reagent to each vial. The vials must be covered with parafilm to eliminate possibilities of contamination. The 3 remaining blanks are prepared in the same manner. Next, prepare 4 standards by delivering 4 milliliters of acid diluent into 4 vials. Then deliver 1/10 of a milliliter of the 100 milliequivalents per liter chloride standard to each vial with a micro pipette. Be sure to rinse the pipette 3 times to the 0.1 milliliter line with the acid diluent. Next, add 4 drops of gelatin reagent to each standard. Then cover the vials with parafilm. The 3 remaining standards are prepared in the same manner. Control and unknowns are prepared similarly. Remember, 4 milliliters of acid diluent, 1/10 milliliter of sample, and 4 drops of gelatin reagent. Then cover with parafilm. We are ready to run a simple blanking and standardization procedure and then determine the concentration of chloride in our control and unknown samples. 6 basic operations are required for each blanking and titration. To blank the chloridometer, first turn the direct reader switch to blank. This will give all readings of blanks in tenths of seconds. Make sure the digital readout reads 0 by depressing the reset bar. Rinse the electrodes. Place the first blank into position. Raise the vial holder until the electrodes are immersed. Turn the Adjust Titrate switch to the Adjust position. Wait for the indicating pointer to fall to its lowest reading. This reading should be less than 5 microamps. Set the adjustable pointer 10 divisions above the indicating pointer. In this case, a reading of 2 microamps, so we would set the adjustable pointer to 12 microamps. Turn the Adjust Titrate switch to the titrate position. When the timer stops, record the tenths of seconds for blank 1. Repeat this operation with the 3 remaining blanks and average the blanking times. They should be within about 1/10 of a second of each other and less than 2 seconds as an average total blanking time. Set the average of the blanking times on the blank timer by turning the knob of the timer until the black indicator needle reads the calculated blanking time. The instrument is now blanked. To standardize the instrument, turn the direct reader switch to titrate. Rinse the electrodes with deionized water. Place a vial containing the standard in the vial holder and raise until the electrodes are immersed. Clear the digital reader by depressing the reset bar. Turn the titration switch to the adjust position. Observe the black needle on the microammeter drop to its lowest position. Again, this reading should be less than 5 microamps. Adjust the red pointer 10 divisions above the black pointer. In this case, the lowest reading is 4 microamps, so we adjust to 14 microamps. Turn the adjust titrate switch to titrate. The blank time is automatically subtracted before readout on the digital display begins. You will note a steady increase in the amperage of the solution as free silver ions pass to combine with chloride ions, and finally a surge at the endpoint when all chloride has been used up. When the titration is completed, record the digital readout. Here, 100 milliequivalents per liter. Run 3 more standards and record the results. They should read 100 milliequivalents per liter. Acceptable deviations are from 99 to 101 milliequivalents per liter. If the standards read correctly, the machine is ready to titrate the control and unknown samples. Consult an instructor if you are unable to obtain consistent standard readings, or if readings are consistently outside of acceptable limits of deviation. To read controls and unknowns, follow the same procedure as standardizing the instrument. Remember, the digital readout records chloride concentrations in milliequivalents per liter when the direct reader switch is in the titrate position. After running the unknowns, the instrument is shut down by a final rinse of the electrodes with deionized water. Turn the machine off. The importance of chloride in the body is evidenced by its role in the chloride shift, the movement of chloride from the plasma into the cell, and vice versa, aids in the maintenance of the acid-base balance. It is very important, therefore, for the laboratory specialist to accurately report chloride values to the physician. Careful adherence to the techniques we have outlined will ensure this accuracy.